So my name's David Britt. I'm a professor of chemistry at the University of California campus in Davis, California. So I'm interested in how photosynthesis works. And from a point of view of fuels in the environment, all of our fossil fuels really started with photosynthesis. So over millions and millions of years, carbon dioxide's taken out of the atmosphere and turned into things like sugars with light energy. Water has been converted to oxygen, so the oxygen in our atmosphere comes from photosynthesis. And fossil fuels comes from the product of those reactions, buried in the earth and turned into things like petroleum over long periods of time. So there's a lot of interest in the biochemistry community in can we harness photosynthesis to make fuels directly. So for example, one thing we might do that we're trying to work on is using light and photosynthesis to split water, H2O, make O2, and then the H's are combined to make hydrogen gas, which can be used as a fuel, for example, in fuel cell automobiles that are coming online now. So that would be a very efficient thing because you take water, turn it into a fuel, and then perhaps use the fuel to just generate water again. So you've got a nice benign energy cycle that doesn't involve carbon, CO2 at all. So that's one of our goals. So my own background is I entered college studying physics, but I was very interested in physics not for pure physics' sake, but learning about what you could learn about the universe, astrophysics, geophysics, biophysics. So when I went to grad school at University of California, Berkeley, I got interested in photosynthesis because as a physicist, light interacting with matter is physics, but this is now an area that took me into biochemistry because we're looking at how enzymes function to, for example, split water and make hydrogen, like I'm saying. So as a graduate student, I started being trained in pure physics, but transitioned into more biochemical work because I was intellectually interested in the fascinating biochemistry of photosynthesis. So one of the things we want to do as a society is reduce our reliance on fossil fuels. And as I think everyone knows now, one problem with fossil fuels is you're releasing CO2 when you burn them. So renewable energy is very important, and it can be done in a biological fashion. For example, splitting water with photosystem 2 and making hydrogen with hydrogenase. But there are many other possibilities for how you can use enzymes to make liquid fuels, etc. So if you make a liquid fuel using CO2 from the atmosphere, even then when you burn it, CO2 comes out when you burn it, but you're just replacing what you had taken out. So it's carbon neutral. You're not adding to the carbon like when you burn petroleum, for example. As the planet increases its energy consumption, we certainly need to look at more renewable fuels. The other thing I would add is, if you learn how these enzymes work, you can actually learn fundamental chemistry from biochemistry that you could apply, for example, to artificial systems, where you take the lessons from biochemistry that all the hardworking biochemists develop in their research and apply it to, for example, things where you might use photovoltaics to harvest light, but you do the catalysis with synthetic catalysts that have been designed on the principles that we've learned from biochemistry. So biochemistry can inform artificial synthetic chemistry as well, allowing you to work with hard materials like photovoltaic cells instead of just working with biological enzymes.